All right, so this is the second lesson. The first, it's kind of like the first lesson. All right, really after this, it gets a lot different. All right, so if you can get, whenever we did the last lesson, when was that? Thursday? Is that when we had class?
Yeah.
So if you can understand that and this, it's probably the hardest part of this whole entire section. All right, the 5.1 and 5.2. So what were the two things that we did in 5.1? It was, what was the first one? What was the first one? Circumcenter and then orthocenter, right? So today we're going to do two, and they have a lot of similarities. Okay, there's a lot of things that kind of look the same, but they're different. All right, you'll see what I'm talking about. So the first one is the Incenter, and the second one is the Centroid. And I'm not going to review the other two just for the sake of time, but we are going to talk about a couple things here. Let's first of all talk about this word. It's called the angle bisector. So if we talked about an angle bisector, that should make sense just in those words right there, angle bisector. So what do you think we're doing to an angle if I find the angle bisector of it? There's an angle right there. If I say find the angle bisector, what am I doing to this angle if I find the angle bisector? What does bisector mean, by the way? Well, more than just connect. Okay, it kind of has something to do with midpoint, but you're not really finding the midpoint. What do you do if I bisected an angle? If I had an angle, let's say this angle is 60 degrees. Okay? And I want to find the bisector of it exactly right. I would take half of that angle. So what's half of 60? 30. So I'm going to draw another, it's not a, I was going to say line, but it's a ray because it starts at the what? What's the point where they come together? The vertex, very good. And then that would be the angle bisector right there, correct? Does that look like 30 degrees? Half of that angle? No. Stop me where you think it's about half.
Right there.
About right in there? Somewhere around in there. It's pretty close, okay? I don't have anything to measure it. Not on this program, I don't. But if that whole thing is 60 degrees, what's this little bit? Oops, I'm sorry. Let's get rid of that 60. So get rid of that, get rid of this. There we go. All right, if the whole thing is 60 degrees, what's this little angle right here then?
30.
That's 30. And what's this angle right here then? That's 30. Okay, so we split an angle into two equal angles. You hear me? Okay, so to bisect an angle, the bisector is it's a ray, right? Because it starts at the vertex and it keeps on going forever. Of course, the sides of the angles are rays as well. So this is an angle bisector when it splits it into two equal angles. It doesn't have to be 60 degrees. Right, it could be anything, but this angle bisector, which is this thing right here, it splits the angle in half, basically, right, into two equal angles. Everybody got it? All right, that's really important. So that's the first thing we're going to use. So guess what we're going to use the angle bisector for? To find the what? The incenter. The incenter, okay? It's right there. So we're going to find the angle bisector to find the incenter. Remember doing that kind of stuff before? What did we do before? We found like a perpendicular bisector, didn't we? And that found something, and then we found something else. What was the other one? Altitude, right? We did the altitude, and that found something. That was the orthocenter, right? The circumcenter was found by the perpendicular bisectors. Remember those two? Yes? Maybe not? Well, there's our goat having fun in the snow. All right, so what we are going to do is bring up this GeoGebra program. And then let's close that. Uh-oh, why isn't GeoGebra showing up? Why isn't it showing up? There's GeoGebra right there. Let's try this again. Let's close GeoGebra and maybe open it up. This is not going to be good because it's not going to show up. All right, there it is there. Let me, oh, there it is. Yay, we got it working now. Okay, don't know why I didn't do it before, but that's okay, it works now. All right, so what we're going to do is we are going to draw an angle bisector. Let's do it on GeoGebra, and then we'll do it on a triangle. I tell you what, let's not even do the angle bisector on GeoGebra. Let's just do the triangle, all right? Because you already saw it. You already know what an angle bisector is, so I don't think we need to do that. So I'm going to draw a triangle. There's triangle. Again, it doesn't matter if it's acute, doesn't matter if it's obtuse or right. It does not make any difference. What we're going to do, though, is we're going to find the angle bisector of each of these three angles and actually have a thing that says angle bisector. See over here on the left? Kira, you watching all this? Not sleeping yet, are you? I barely started. All right, so angle bisector. So if I want to bisect this angle, watch what I do. I click on this side and I click on this side, and then look what it did. It made an angle bisector. I don't know why it makes that line right there. This line is perpendicular to that angle bisector. I'm not sure why they do that, but that's what they do. So what I'm going to do is do this real quick. Yes?
It doesn't look like it's half of
It
that.
is. I'll show you in a minute, okay, why it is. But this angle right here and this angle right here are exactly the same, okay? And they are. So there's an angle bisector, so I split angle B in half right there, and then I'm going to come down here to angle C, click on this one, and I split that in half. So they all meet at a point. How about that? The other two met at a point. Remember circumcenter? They all met at one point, and the orthocenter, they all met at one point. Well, guess what's true about this? They all meet at what? 1 point. What do we say about those lines? They are what to each other? Give me a good geometry word. Starts with a C.
Congruent.
No. They're concurrent. Right. When they all meet at 1 point, they're concurrent. So what I'm going to do, is put a point right there, and then, click on this, I'm going to name it. Guess what I'm going to name it? Let's name it Incenter. How about that? It's a good name for it, right? All right, so that's our Incenter right there. So let me get rid of all this other mess. So this takes a second. Let's get rid of that. Let's get rid of it. See how it highlights right there, and I can just click on it to right there. Shh, stop. You don't need to do that. Just stop and listen. Okay, one more to get rid of. Guys, you still hear a lot of talking. All right, so there we go. That's our Incenter. Now, there is something special about this Incenter. Remember we did circumcenter? There was something special about the circumcenter. Do you remember what was special about that? It was equidistant to the, anybody remember? Look in your notes if you have to. The circumcenter was equidistant to the vertices, right? The three vertices, okay? The orthocenter, what was special about the orthocenter? Nothing. There's nothing special about it, okay? It feels bad. It's probably got a complex, but that's okay. Orthocenter, there's really nothing special about the orthocenter. They are concurrent, right? They all do meet at 1 point, but it's not like equal to anything. Orthocenter, there's really nothing. But the Incenter, there is something that's true about this. And the Incenter, listen very carefully, you might want to write this down. The Incenter is equidistant, which means it's the same distance, to all three sides of the triangle. Write it down. Logan, you're not writing it down. Write it down. Why do I have to say your name? The Incenter is equidistant from the three sides of the triangle. E-Q-U-I, and then distant. It's equidistant, E-Q-U-I. That's equal. That's it's a word that we use to mean equal. It's the same distance, equal distance to the sides. So what is the distance, though, from this point to this side? Well, I'm glad you asked, because I'm going to show you real quick here without the triangle. What if I had a line like this, and then I had a point just somewhere random outside of that line right there? If I asked you to measure the distance from point F to line segment DE, what would you do? Straight down. Give me a better word than straight down. Yeah, perpendicular. That's what I'm looking for, okay? So what you want to do is measure it so it's perpendicular. Would that be the distance? No. Would that be the distance? Could it be anywhere on here? No, because then it would be all different distances if they could be anywhere, right? So when I talk about the distance from a point to a line or a line segment, it has to be the what? The perpendicular distance, okay? I'm going to get rid of that, and I actually have a thing this perpendicular line. So I can click from this point. I can click anywhere on this line segment right here. Boom, it made a perpendicular line. Do you see that? So what is the distance though? Is it the whole entire line? No, it's from, let's do this. It's from point F to point what? G. So let me just do that. So F to G. All right, and let's get rid of this big long line right there. Boom. There we go. That's what I want. Okay, so what is the distance from point F to point DE? The line segment FG. Whatever that length is, okay, that's the distance. Agreed? So watch this. I could find the length of it. I got a little button right here. If I click on it, it finds me the length of that line segment. It's 3.4. Okay, now watch this. What if I take this? Oops. Yeah. I can move this over here. Depending on how I move this thing, that distance changes, doesn't it? Okay, but notice what's always true about FG. FG is always what to this DE? It's always perpendicular, isn't it? Okay, you find it? You understand that? So that distance could change, right, depending on how close that point is to that line segment. Okay? Now, with all that said, let's go back up here. What are we trying to do? What did I say was true? What did I say was unique about the Incenter? It was what? Equidistant to the sides of the triangle. So what length is that? It's from the Incenter. Where? How does it hit it? It hits the side, but where does it hit the side? Perpendicular. That's right. Okay, so guess what I'm going to do? I'm going to put perpendicular line. I'm going to go from the Incenter to anywhere on this line. Now look, this program, I just click anywhere on it. Look what it did. It made a perpendicular line, didn't it? Okay. I'm going to do that to all three. So I'm going to go from the Incenter to this side right there. See how it's perpendicular right there? Then I'm going to go from the Incenter to this other side right here. And notice about all three of those lines, okay, well, yeah, they would all intersect. That's not anything special. We already talked about the Incenter. It's special because, anyway, forget that. So now let's get rid of those big old long lines. Actually, let's do this first. Let's draw a segment from the Incenter to there. Let's go from the Incenter to here and the Incenter to here. All right, now I can get rid of those big old long lines because they just kind of are ugly, get in the way. So let's get rid of that one. Let's get rid of this one. And let's get rid of this one. All right, and now we got those three right there. Now watch, if I move this around, notice, what does it seem like all three of those distances, do they look like they change? I mean, if one gets shorter, if one gets smaller, does just one get smaller and the rest stay the same? No, they all stay the same. If this gets bigger, then all three of them get bigger, right? So what do you think might be true about all three of those distances? They're equal. Let's see if they are, okay? So let's go to distance or length. Let's click on this. That's 3. That's 3. And guess what? That's 3 right there. Okay? Everybody see that? So now, if I click on this, see? It makes it smaller, makes it bigger. Now, what if I made it obtuse? Is the Incenter, remember how we did the circumcenter and orthocenter? If I made it obtuse, the circumcenter would be outside the triangle, right? If I made it into a right triangle, where would it lie? It would lie right on the triangle, okay? But this, no matter if I make it look like a right triangle, that kind of looks like a right triangle there at C. Okay, where's the Incenter? It's inside the triangle. It's always going to be inside the triangle. Look, it's always, always, always going to be inside the triangle. Do you see that? All right, so the Incenter will always be inside the triangle. I want to show you something that I showed you on the circumcenter. Do you remember on the circumcenter, I drew a circle? Do you remember that? And the circle did what? It went on the outside of the triangle. Well, it actually, all 3 points of the triangle were on the circle itself. Do you remember that? So it was circumscribed. right? That's why we call it the circumcenter or circumference. What's circumference? The distance around something, right? But this is an incenter. So where do you think the circle is going to be here? Do you think the circle is going to encompass the whole entire triangle? It's going to be where? It's the incenter, so it's going to be, what do you think? Inside of there. So I can click on this button right there. It says circle. It says circle with center. So here's the center right here. And watch, I'm going to make the circle, and then it's going to hit right there. So now where's the circle? It's not on the outside, it's what? On the inside of it, okay? Since all three of these distances will always stay the same, all three of those distances are the what of the circle? No, come on. No, it's not perimeter. Perimeter is the distance around it. Look, what's that 3.2, 3.2, 3.2? Starts on the center and it goes where?
To the side.
What if I went from here to here? What would that length be? It's the radius. It's the radius of the circle. Okay, so look, no matter how I draw this, that circle stays inside of the triangle, and look at the radius of the circle. That's always going to be the same. And that must be true, right? Every radius on the circle. I could draw 100 different radii from the incenter to a point on the circle. They'll all be the same exact. Let's just do it just for fun. Watch. If I go from the incenter to here, what do you think the length of that's going to be? It should be 3.1 if I don't move it, right? Boom, click it. Sure enough. I could do that 100 times, couldn't I? I could do it 1,000 times. I could do it 1,000,000 times. I'm not going to. I will do it 4 times and that's it. Okay, so that's all we have. So that is the what? The incenter. What's true about the incenter? The incenter is equidistant from the what? Each of the sides, right? Each of the sides of the triangle. Okay, that's something that you're going to have to remember. All right, it's not that easy to remember. I don't have I've actually looked it up. I've looked it up on Google. I looked for a long time on Google to try to find a way that we can remember what's unique about a circumcenter, an orthocenter, an incenter, and then the centroid, which we're going to do in a few minutes. Okay, but there's really there was a couple people that put some stuff on here. You know how in Algebra 1, did you do the FOIL method? Do you remember the FOIL method? Okay, first, what would it stand for? First, outer, inner, last. I say inside, outside, but it's the same thing, right? First, outside, inside, last? Yes? Okay. That's like a nice, easy way. Remember order of operations. My dear what? Aunt Sally. Okay, you remember that? Please excuse my dear Aunt Sally. Yes? All right, so PEMDAS. Those are nice little ways, little tricks, little memory devices so you can memorize how it works. There's really nothing good to learn these things. You just have to remember them. That's it. Okay? I looked it up. I don't know, one lady had this video, and I'll tell you what, it was way harder learning the little memory device than it was just to memorize what's true about them, right? It was like, my little goat ate something. I don't know. It was something weird like that. And I was like, how in the world are you going to remember that? That's crazy. Just memorize the thing, all right? And that's what you're going to have to do. You will have to remember it. So I promise you, on the quiz, you're going to have the first 4 questions on the quiz are going to ask you about a circumcenter. It'll say something, I forget exactly how it's worded, something about being concurrent. And so like circumcenter, what's unique? What's special about the circumcenter? It's equidistant from the what? From the vertices, right? So what I'm going to have is, okay, tell me the name or tell me the word. I forget exactly how I phrase it, but tell me the word that represents the, what did I just say? I forget exactly how it's worded, but it's in the quiz. But you're going to have to write, it'll say the distance from, or the blank is the distance from the point of concurrency to each vertex. And what would that be? That'd be circumcenter. Then you got another one, like this one right here. It's what's equidistant to the three sides of the triangle. What would that be? That'd be the incenter, okay? So I'm going to ask you the first 4 questions, just me fill in the blank, and you got to know the words that go with it, all right? You just have to know what word goes with what sentence, all right? So it's really important that you know that. All right, enough of that. Let's, tell you what, let's just clear this. I think we're good with Incenter. So we're not going to save it. Let's do another one. You guys, are you driving yet? Some of you guys are starting to drive anyway. But you ride in cars, though, don't you? And you look out the window. So stop. It's not a conversation. So you're riding down the road, like on Route 40 a lot of times. It goes east and west, right? Riding east, riding west. In the middle of a lot of Route 40, not the whole entire road, but a lot of Route 40, there's this big grassy area in the middle of it. Agreed? Right? And you're not supposed to cross it and all that kind of stuff. What do we call that big grassy area in the middle of a road? Call it the median. Call it the median. M-E-D-I-A-N. All right? Everybody got that? So we call it the median. What is it? I got a road here and a road here. The median is the part that's in the what? The middle. Okay? It's not always in the middle because sometimes you'll have traffic with like 4 lanes. Not on Route 40, but traffic with 4 lanes, maybe traffic with 2 lanes. So it's not always in the middle, but that's basically what it means, right? That's why they use the word median. I had a guy that I knew, he was actually my youth pastor a long time ago. We were playing flag football or something, and then the ball went out into the median. He says, oh, the ball went out into the medial. He called it the medial strip. We used to call it the median strip, right? The strip of grass. He called it the medial strip. And even back then, I think I was in maybe college or something. And I was like, oh, and I felt bad. I didn't want to like correct him or anything, didn't want to be rude. But he said the medial strip. And I've heard other people say that too. It's not medial, it's what? Median. M-E-D what? I-A-N. M-E-D-I-A-N. All right. So what does that mean? It basically means the middle. So if I was to draw a triangle, boom. Oh no, I can't use this. See, every time I use that pen, it just draws a line. No, we're good. We're good. So watch. What I'm going to do is I'm going to draw the median of all 3 sides of the triangle. What does that mean? This means I start at a vertex. Everybody hear me? I start at a vertex and I go to the other side, but where do you think I go to the other side? Think of the word median. What do we say? It's in the what of the road? In the middle, that's right. So what am I going to hit right here? I'm going to hit the middle, okay? Or give me good geometry. We don't say middle, we say what? Midpoint. Right, we go to the midpoint. All right, so there we go. So I'm going to hit the midpoint of this side. Boom, right there. There's the midpoint. You hit the midpoint of this side. Right there, it's at E. Then the midpoint of this side. There it is at F. Let's just move this to the outside. Move this to the outside. Okay? Now what I'm going to do is I'm going to connect, everybody watch, from the vertex to the what? Midpoint. And what line do I have there? I got line segment AD. What is that? That is the... No, it's not altitude. Altitude goes perpendicular. What did we just finish talking about? The median. It's called the median. That's right. It's the line segment that goes from the vertex to the midpoint of the opposite side. You writing any of this down? Many of you are. Some are not. Some refuse. I don't know why. You got nothing else to do. There is absolutely nothing else to do in here. Just write down what I'm saying. Yes. The median, it's a line segment that goes from a vertex to the what? Midpoint of the opposite side. All right? So AD is a median, BE is a median, and what's my other median? CF right there. So all 3 of those are medians. Check it out. What do all 3 of those medians do? They intersect, right? So that means all 3 lines are what? Good geometry word, starts with a C. They're concurrent. They're concurrent because they meet at a point.
Wait, what is a median again? Oh, are you dumb?
Shut up. Don't talk to me like that ever again, please.
Oh, you got freckles, big nose, and fluffy hair, yeah. What?
So a median, it's a line segment. It could be a line, but in our situation, it's a line segment, okay? That go, in fact, we're not ever going to say line on this, what we're talking about right here. It is a line segment that goes from a vertex of a triangle to the midpoint of the opposite side, okay? It's a line segment, right, that goes from the vertex to the midpoint of the opposite side. That is a median, all right? So guess what we call point G then? What was the name of the lesson? We already did one of them. No, that's not the name of the lesson. Centroid. That's right. So it's the centroid. So let me click on this, click this, click this. All right. So I'm going to, instead of calling it point G, I'm going to call it the centroid. All right. So there you go. So that's the centroid right there. Now I'm going to keep those line segments there. I'm not going to erase them. Here's the thing that's unique about the centroid. Everybody watching? What I'm going to do, actually I will get rid of the whole thing because here's what I'm going to do. I'm going to actually draw a line segment from, let's go from point F to the centroid. I think I clicked it. And then from point C to the centroid, right there. And now I'm going to get rid of EC. Let's see. I think, yeah. Yeah, there we go. So now look, I've got this. See how I got that line segment right there? Yeah. That's from F to the centroid and then from C to the centroid. So I got those separated. All right, so it's not just one big line. And I'm doing that for a reason. Because there's a relationship. Listen. There's a relationship between this from F to the centroid and from the centroid to C. There's a relationship between those two. All right. What do you think might possibly be true about this segment right here and then this segment right here? Do they look equal to each other? Supplementary. Supplementary means they do what? They're angles. These aren't angles. Supplementary means angles that add up to 180 degrees. So they're not supplementary. They're definitely not equal. Look at from F to C and from F to the centroid, from the centroid to C. Do they look the same? Do they look the same length? No, absolutely not. In fact, this one looks considerably bigger than this one. And in fact, it's not just considerably bigger, it's exactly, what do you think? Just wild guess. 2 times bigger. It's exactly 2 times as big as this. Okay? So let's continue drawing some line segments. So let's go from A to the centroid. And let's go from D to the centroid, right there, okay? And now, and let's do from B. Might as well do them all. B to the centroid, E to the centroid, and now, it doesn't look like I did anything different, but I really did. I did separate them. And let's go to this. Let's click on that line right there. That's the whole thing, so I can get rid of, oops. I messed up. What did I do? Did I not put my, yeah, I messed up. But I think I did this one right. Yeah. There we go. Let's get rid of that one. Nope. What did I do? Let's try this again. I was on a roll. I was doing so well until right now. All right, let's try this one more time. There we go. Let's go segment. Let's go from B to there, and let's go from E to there. There we go. All right. And, you know, it might be easier if I just get rid of that line. Oh, no, it's this one, isn't it? Yeah, let's get rid of that. And then I can do a segment. Give me just a minute. Oh, I'm almost there. From there to there. There's a reason I'm doing this, promise. And from there to there. Okay, now I have separated them all. Okay, they're all, oops. They're all separate. See how that highlighted? It's hard to tell, but that highlighted. and that highlighted right there. Okay. And watch, if I move this around, see how the centroid always stays inside of the triangle? Doesn't matter if it's obtuse, doesn't matter if it's right, doesn't matter if it's acute. Centroid always stays inside. The same was true with what? The incenter, right? The incenter, that was true as well. So what I want to do here, we're almost done. What I want to do is I want to find the length. Now this may not work out, I'll show you why in a second. This may not work out perfectly well at first, but you'll see that it does. So let's find the length of that. It's about 4.5. So we said this should be what? Twice as much. So if I click on that, now they say 9.1. That's because the decimals might be off a little bit. So I can always come up to here, if I remember, settings, and then where do I go? I forget now which one. I think I go to this. There we go. See, I'm only at 1 decimal place. If I took this to like 2 decimal places, that might be a little bit more accurate. All right, if I go to 3 decimal places, it might be even more accurate than that. So let's go 2 decimal places. And if I move it around a little bit just so that, oops, get rid of that, get rid of this. There we go. See, that's 9 and that's 4.5. Okay, so this is twice as big as this. Or this little bit is what of the bigger one? It's half, okay? You could also look at it like this. The little one is how much of the whole entire one? No. Well, of the whole entire thing. This is not half of the whole entire FC. Say it. It's 1/3. Very good. That's good. Okay, not many people get that. But that's 1/3. See this little part right here? That's 1/3 of the whole entire thing. So how much is 9 of the whole entire thing? It's 2/3. That's right. So we got a 1/3 and we got a 2/3. 1/3 of what though? 1/3 of the whole thing. 2/3 of what? The whole thing. Okay? Or you could look at it as this shorter one is half of the longer one. Not the whole thing, but the longer one. Did I confuse you yet? All right. So the short one is half of the longer one. Or you could say the short one is 1/3 of the longer one. All right. So let's do this. Let's take this, see if I can get a 12 out of that. Good. All right. Let's do the math. What's the whole entire length, FC? 18. So 6 is what of the whole thing? 1/3. Is 6 1/3 of 18? Yeah, because if I took 1/3 of 18, 18 divided by 3 is what? 6. It works, doesn't it? Okay. What about 2/3? Do you know how to do 2/3? Well, it's just 1/3 times what? 2. Right? So what's 1/3 of 18? 6. What's twice of that? It's 12. Yeah, boom. There it is. All right. I could also do these lengths right here. And again, they may not come out perfect because of the decimal approximation. That's 3.3. You'd think that would be 6.6, wouldn't you? Okay, but it's probably not exactly 3.3, right? But they just rounded it to 3.3. Okay, you with me on that? So on these numbers, they may not come out exactly the way they're supposed to. That one does. This one doesn't, just because of the decimal approximation thing. All right, but you do get the idea. All right? And that is Centroid. I used to do a little demonstration with Centroid, and I don't think I have it. I might have to make another one. Basically, I took a cardboard cutout of a triangle. Doesn't matter what kind of triangle. And what I did is I found the midpoint of all 3 sides, and I connected a line, right? So I made the median of all 3 sides, and I found the centroid. What that does is this. If I take a triangle, and I took a pen, and I put it, right at the centroid, that's actually called the center of gravity. That's where it will balance. You can take any triangle at all, right? Find the centroid, put a pen there, all right? And it should balance the triangle right at that point. And that's kind of cool about the centroid. So it doesn't matter what the shape of the triangle, oops, let's do this. It doesn't matter what the shape of the triangle is. If I put a pen right there and I held it flat, okay, it will balance right at that point. And it's pretty easy to do. You just take a triangle, cut it out with, now regular paper is not going to work because it's all flimsy, right? And it'll just flop over. But if you take cardboard, even like cardstock paper is not very good. But if you take some cardboard and you cut out a triangle and then you found the midpoint to all three sides, you connected the vertex to that midpoint, they should all connect at one point. That would be the centroid. Then you can take a pen or a pencil or something like that. Usually I use a pencil with an eraser because it adds a little more friction to it, right? And I put it at the centroid and boom, right there. It'll balance perfectly. We call that the center of gravity, okay? All right, so you have homework. It's 1 to 12, page 217. All right, so that's your homework. Have both of those. Have 5.1 and 5.2 finished for tomorrow, and we'll go over both of those tomorrow.